Then there are mainly two kind of walls. um, Let me write them. Mm, Adiabatic wall, or it has another name also, thermally insulated. Two names of the same thing. uh, what does it mean? Through this wall, hmm, through this wall, heat cannot communicate. Meaning heat जो प्रोसेस होगी ड्यूरिंग द एक्सचेंज ऑफ एनर्जी, हीट कैनॉट गो थ्रू, और यू कैन से transfer of energy cannot happen in the adiabatic and thermally insulated wall. Second type of the walls are conducting wall, or someone call it diathermic wall. So in this case, through this wall, heat can communicate. Meaning that the energy can be transferred from one system to another system if the wall between the two system is diathermic wall. So let me show you one thing. Suppose this was the system 1, system rather call it A, and we had another system B. And when I'm saying this is a system, it can be anything, gas or something else, but we have we have inserted a boundary. That boundary is, or you can say the wall is adiabatic wall. And in the most of the convention, the adiabatic walls are always drawn like this diagonal, like this. They make diagonal like this. So now what will happen? There will be no transfer of energy. Suppose it has initial energy of 10 joule and it has initial energy of 12 joule. And if you place a adiabatic wall between these two systems, the energy will not change as time passes. Now the adiabatic wall, examples are the adiabatic wall. For example, we can have a wood, or cotton, or something cement, some object made with cement, etc., etc., or lead, maybe like this. On the other hand, we can have a wall, we can have a wall through which the energy can pass through. Energy can go from one system to another system, that is, heat can communicate. Okay, mainly they don't draw any diagonal line when there is a wall, but it is a convention. But they have to write what kind of wall they have drawn. So if this is diathermic wall, for example, we can have any metal conducting medium, suppose copper, lead or aluminium. Okay, so these are two kinds of wall, mainly two kinds of wall that we see. Why we are reading these kind of walls, you will see further. Fine. So now we come to a very important point, that is called thermal equilibrium. Okay, thermal equilibrium. uh, Before going to thermal equilibrium, let us go to mechanical equilibrium, right? We have seen in our mechanics courses also that suppose I have uh, mm, I have a pendulum like this. So if you see, and the length having the length L of string and mass m, so of the bob, so there is a force on the bob in downward direction, that is gravitational force, and tension force is around in the opposite direction, that is T. So what is the equilibrium position, I mean not position, what is the condition for equilibrium here? The condition for the equilibrium here is that the force acting on the bob has to be equal and opposite, right? That is the condition. So every equilibrium situation or state, every equilibrium state, doesn't matter it is thermodynamics, mechanics, or some other field, electromagnetism, something else. So every equilibrium state is decided by some physical quantity. For example, here the force is that physical quantity. And for mechanical equilibrium, right? For mechanical equilibrium, mg equals tension, right? But this was only a single system. Suppose I can give you another system. Suppose I am having a small beaker, not beaker, any container, and they are connected by a valve. Okay, like this. Fine. It has some gas inside this. Let me not draw like this. It has some gas inside this, and this also has some gas inside this. Fine. What do you mean by gas? There is a particle of gas particles, and in between of the valve, these two container, I have put a small holder like this, right? So you can see that particle of this gas will go from here to there, and this wall particle from this system will also come along this direction. So what will happen, this valve that I'm saying as the, any, you can call it a valve only, VOLVE, valve. So this can, and it can move, like suppose the force from this is very high, it can go here, and if the force is going to be high from this side, it will go here, right? So after some time, I mean after maybe some 10 minutes or something else, so what will happen, it will stop moving, right? It will stop moving, and that situation when it stop moving is called equilibrium, mechanical equilibrium condition. Then this is called at mechanical equilibrium condition. Fine. But now the way we had a force here, force for determining that equilibrium has achieved, what is the corresponding quantity here? that is pressure. Suppose this gas is called A, gas A, and this gas is B. So at equilibrium condition, at mechanical equilibrium condition, or you can say it like this, condition at mechanical equilibrium is PA, pressure of A, equal to pressure of B. So are you able to make some analogies? Like, I'm saying that equilibrium is a very general concept, and there is a criteria to decide that a system is in equilibrium or not. So we have seen two examples. In one case it is a force, and in another case it is a pressure, and although pressure and force are not two different quantities, but yeah, for mechanical equilibrium we mostly think about the force, not pressure, sorry. For mechanical equilibrium we just focus upon pressure. Now what about thermal equilibrium? What is the quantity that decides uh, the thermal equilibrium? An important thing is that you can't guess these things in advance कि भाई मैकेनिकल इक्विलिब्रियम के लिए प्रेशर होता है और थर्मल इक्विलिब्रियम के लिए कुछ और होता है. You can't guess these things in advance. You don't know. You need to do experiment, and after that experiment you can deduce what is the quantity that remains constant, that remains same, or rather not constant, but that remains same. Like here the pressure remains same, pressure of A equal pressure of B, suppose some number 100 pascal, something like this. So this number remains same for both the system, for system A, for system B, something remains same, right? So I am saying that for different kind of systems there is different kind of quantity. So we need to perform experiments in order to find out what that quantity is. So the zeroth law of thermodynamics is that kind of experiment that proved, or not proved actually, there is nothing to prove, that give us a result, right? That give us a result that the temperature is a quantity. The temperature is the physical property of a system that remains same for every system if these systems are in thermal equilibrium. Okay, I think now you are able to connect the dots. I'm saying that for mechanical equilibrium the pressure of the system is same. Similarly, experiment shows that for thermal equilibrium the temperature of different systems remains same, and that is the zeroth law. In the one way of saying the zeroth law, there are many ways to saying zeroth law, but let me write the statement. And whatever I have told you, that is not exactly the zeroth law written in the books, but this is also written, or you can say this is also called the zeroth law. If you see the definition in the book, that they remain like this. They write in this way. Statement is that if two system, suppose X and Y, are separately in thermal equilibrium with another system, say Z, then they are in thermal equilibrium with each other, meaning X and Y are also in thermal equilibrium. And one more thing I have forgot to mention, that what do you mean by equilibrium? How do we identify what is the meaning of equilibrium? Maybe you have seen, you have some definition, but equilibrium is something then when the state of it is a particular state of the system when physical properties do not change, right? Suppose in case of pendulum, the physical property is the displacement or the position of the particle is fixed, it is not changing. Here also the position of this valve is not changing, so that is called equilibrium position, equilibrium thing, something called in the equilibrium case. So now if you see, what does it saying, this law is saying that suppose you had two system, this is x, this is y, and they were in the thermal equilibrium uh, with the third system, that is z. Okay, and we have put a which kind of wall in between these two objects. This is diathermic wall, but between this thing, between x and y, we have put a adiabatic walls. Why we are doing this thing? Because now what I am trying to do here, we want to see how it is experimentally seen. This was experiment. So what do we see that let me write also what kind of wall we have to make here. The first one is adiabatic, this one is diathermic. Okay, now since x and y cannot communicate, okay, the energy cannot transfer between x and y because we have adiabatic wall, and here we have diathermic wall, but it means that x can communicate with z and y can communicate with z. So what happens at t equal to 0, the moment we have started with this experiment, the heat will flow from a to heat will flow from x to z, or whatever is having higher energy, right? Because energy is going to transfer from one place to another place. So energy will transfer, like suppose the z is having very high energy. Out of all xyz, z is having highest energy. So what will happen when we try to start this experiment? The z will lose energy to x also and y also. The way we saw that the particle will move from here to here, the same way the energy will be going from here to there. In which form? In the form of heat, right? That is the mode of transfer is heat here. Here is no work right now. So energy will be transferred from here to here, and after some time there will be no transfer of energy. The experiment has shown this. After some time, in experiment we have seen that after some t equal to t time, and this was the situation at t equal to 0. T means time. After time t equal to t, transfer of heat stopped. And I told you that what is the meaning of equilibrium, and this is called this is the situation for equilibrium, because I have told you that when there is no change in physical property, that state is called equilibrium. So if there is no changing in energy, so this is called equilibrium situation. Now what does it mean? X is in equilibrium with z and y is in equilibrium with z also. So this is the first half of the statement. So after this, what we have seen, we just exchange the walls. In the second part of the experiment, what do? We just exchange the walls. Step 2. If we just exchange the walls, diathermic is here And let me make that walls first. And this one, this is diathermic, and this one was adiabatic. Fine. So we just swap the two walls. Sorry. So what is the possibility? Now these two cannot interact, right? There is no communication, but there can be communication, right? Because the wall is allowing them. But experiments showed us that there is no communication. There is no communication. What does it mean? If there is no communication, if there is no change in the property of the physical property, then these two are also in equilibrium, thermal equilibrium. So we observed that x and y do not communicate, or do not exchange the heat, or it is bad way to write, do not transfer, or rather there is no exchange of energy. Right? There is no exchange of energy, which means x and y are also in thermal equilibrium. And here what we say, that after some time t, the heat transfer stopped. And what was the conclusion? It means that x and z also, y and z are in thermal equilibrium, because there is no halchal in the system, there is no physical property changing in thermal equilibrium. So what do we see? In the step 1 we have seen that x, z and y, z are in thermal equilibrium, and in the second step we have seen that if this is true, then the x and y is also in thermal equilibrium. So having these things, we have seen that experimentally that thermal equilibrium is like this. And also we have deduced that there was a quantity that is we have seen that temperature that was not changing. So I think that part I have written. No, I have not written. So let me write this thing. So and this is also called the second statement of statement 2 for first zeroth law. That is, there exists a physical quantity or physical property called temperature that tells us when two systems are in thermal equilibrium. Okay, so you can say this is the kind of definition of temperature. Temperature decides that the given systems are in thermal equilibrium or not. Temperature decides that whether the I have written weather here. Fine. Like we have seen that pressure decides that two systems are in mechanical equilibrium or not. Fine. So this is what all about the first zeroth law and equilibrium position, heat and energy and work, or mathematically a mathematical statement. Zeroth law कि if temperature of A and temperature of A means system A, and there are suppose A, B and C are three thermodynamic system. Let A, B and C are three thermodynamic system, and A temperature of A is equal to temperature of C. Also temperature of A temperature of B is equal to temperature of C. It means temperature of A is equal to temperature of C also. And if you see pure B, and if you see by pure mathematics, this is called transitive property, na? Transitive property, you must be aware of this mathematical property of in algebra, in the arithmetic, not algebra. So we can say that temperature follow ट्रांजिटिव प्रॉपर्टी कि मान ले अगर x बराबर y है, फाइन, और z बराबर भी y है, तो इसका मतलब कि x और z भी बराबर हैं. दिस इज द मीनिंग ऑफ ट्रांजिटिव प्रॉपर्टी. Fine, this is all about the first law. Sorry, this is zeroth law, not first law. And again, this zeroth law, you must be wondering that this law is starting from number 0. It is too weird. Yeah, this is just because of historical purpose. People realize that this thing, this thermal equilibrium is determined by temperature. They discovered, or they come up with this idea later, when the and before that, all the laws of thermodynamics, law 1, law 2, law 3, they were already discovered and published to society. So they need to, because it was very fundamental, then they can't give it a number like thermodynamics 4th law or something like that. So it was too fundamental, and it was defining the definition of temperature, so they had to give it the name as zeroth law.